Today we are going to discuss about instrument transformers. Especially we are focusing on current transformer in this part 1. Now the question arises basically what is an instrument transformer? Well, basically it's a transformer that is used in conjunction with any measuring instrument that could be ammeter, voltmeter or any protective equipment. The most common usage of instrument transformers is to operate instruments or metering from high voltage or high current circuits, safely isolating secondary control circuitry from the high voltages or currents. It also utilizes the current transformation and voltage transformation properties to measure high AC current and voltages. Now, we are going to discuss about the types of instrument transformers. Well, the instrument transformers are basically categorized into two types. One is current transformer and the other one is potential transformers. A CT is a current transformer and the PT is a potential transformer, or you can say the voltage transformer. The standard transformers like distribution transformer or power transformers do not have CTs and PTs. CT alone are used at commercial and industrial level, um, who consume large amount of electricity, and for this the current is stepped down so the meter can read it. For example, a turn ratio is basically about, for example, a 200 is to 5 or 40 is to 1 ratio. That means if the real load is 40 amperes, so it converts into 1 ampere or 5 ampere. So whatever the meter reads, you would multiply it with the multiplying factor. CTs and PTs are used in primary metering configuration. Most meters cannot withstand high voltages and currents, so the configuration is used to bring the voltage and current down to a level the meter can read. As we discussed in the last slides, what are the major tasks of instrument transformers? So, if we talk about first three major tasks of an instrument transformers, the first task is basically to transform current or voltages from usually a high value to a value easy to handle for relays and instruments. As we know, for example, if we have a distribution setup of 400 amperes, so we cannot design relay of 400 amperes because it is almost impossible to design such a large relays, and also it is not cost effective. Secondly, to insulate the relays, metering and instruments from primary high voltage systems. Along with that, the third one is to provide the possibilities of standardizing the relays and instruments to a few rated current and voltages. As we know that uh, if we talk about standards like American national standards, there are some standards set for the relays. Like relays have to operate in 12 volt for electronic systems, or if we talk about power systems, so it may be 110, or if we talk about CTs, it may be from 5 ampere or 1 ampere. If we talk about application of instrument transformer, there are several applications of instrument transformers. Instrument transformers are used in AC systems for measurement of electrical quantities that may be voltage, current, power, energy, power factor, frequency, or many other factors. Instrument transformers are also used with the protective relays for the protection of the power system. Basic function of the instrument transformers is to step down the AC system voltages and currents. For specially constructed high voltage instrument transformers, to insulate the high voltage circuits from measuring the circuit in order to protect the measuring instrument from burning. Students, I can also say that instrument transformers play a core role uh, in any industries or grid stations. As we mentioned in introduction, that this part is basically belongs to the current transformer. Current transformer is a type of instrument transformer that is designed to produce an AC current in its secondary winding, which is proportional to the current being measured in its primary. This current transformers only deal with the currents and different ratios. If we talk about the types of current transformers, the current transformers are majorly categorized into two types. Uh, One is wound primary type and other is bar primary type. In the last slide, we discussed about the types of transformers. In this slides, you can see on the left hand side, you can see the wound type current transformers, and on the right hand side, you can see the bar type current transformer. So, if we explain one wound type current transformer, basically the wound current transformers uh, is physically connected in series with the conductor that carries the major current flowing in the circuit. The magnitude of the secondary current is dependent on the turns ratio of the transformers. So, as the bar type current transformers is concerned, this type of current transformer uses the actual cable or bus bar of the main circuit as the primary winding, which is equivalent to the singleton. They are fully insulated from the high operating voltages of the systems and are usually bolted to the current carrying devices. In this slide, you can see the internal view of CT. This CT is basically a bar type current transformer. On the left hand side, you can see the CT of ratio 1 is to 12. So the primary side has 1 and the secondary side have 12 turns. So it comprises of 1 is to 12. On the right hand side, you can see it's basically a ratio of 2 is to 20. So we can say that on primary side you have 2 turns and on the secondary side you have 20 turns. Similarly, there is one more example of bar type CT. You can see on the left hand side there is a ratio of 3 is to 12, and on the right hand side you can see 4 is to 9. So we can say on primary side there are 4 turns and on the secondary sides there are 9 turns. It is important to know uh, that how CTs are look like on the grid station. On the left hand side you can see the long bars which depicts the CT. Well, the outer part is basically the porcelain insulation that protects it from external hazards or external links. Um, well, the basic problem is that for the students that how we can identify on grid station that what is CT and what is PT. So they are basically confused because both look like a cylinder of porcelain insulator with top cylindrical box type connection, head and cylindrical square type metal box base. Well, the important is connection, as CT is having thick bar primary connected in series between transformer secondary and bus bar can easily be judged, while the PT potential transformer places on side looks having only low current input, wide connection, and connected in parallel. If we talk about equivalent circuit of the current transformer, there are two major components. Number one, an exciting current which magnetize the core and supplies the eddy current and hysteresis losses. Secondly, a remaining primary current component which is available for the transformation to secondary current in the inverse ratio of turns. Uh, in next slide, we will talk about the explanation about the equivalent circuit of the CT. The equivalent circuit of the current transformer is similar uh, to the ordinary power transformer, but some of the problems in this equivalent circuits, basically, the exciting current is not being transformed and is therefore the cause of the transformer errors. The amount of exciting current drawn by a CT depends upon the core material and the amount of flux that must be developed in a core to satisfy the output requirements of the CT. That is obviously to develop the sufficient driving voltage required, pushing the secondary current through its connected load or burden. Magnetizing curve. Well, this curve is divided into basically three sections. Now, the one is initial region, other is unsaturated region, and the third one is saturated region. This curve is the best method of determining current transformer's performance. It's a graph of the amount of magnetizing current required to generate an open circuit voltage at the terminals of the unit. Well, uh, due to the non-linearity of the core iron, it follows the BH loop characteristic. In the last slide, we discussed about the magnetizing curve. Uh, well, on the right hand side, you can see uh, in the picture circles knee point. Well, the knee point voltage basically is a transition from the unsaturated to saturated region of the open circuit excitation characteristic, which is a rather gradual process in the most core material. This transition characteristics make a CT not to produce equivalent primary current beyond certain points. This transition is defined by knee point voltage in a CT, which decides its accurate working range. Well, uh, it's generally defined as the voltage at which a further 10% increase in volts at the secondary side of the CT requires more than 50% increase in the excitation current. For most of the application, it means that the current transformers can be considered as approximately linear up to this point. Well, metering current transformers are used with the measuring instruments such as ammeters, voltmeters, kilowatt hour meters. There are two purposes uh, of using metering CTs. Number one is to isolate the instruments from the power circuits, and the second one is to standardize the instrument. Usually, for the current transformer, it's about 5 ampere to 1 ampere. Instruments and meters are required to work accurately up to the full load current, but above this, it is advantageous to saturate and protect the instruments under fault conditions. As we discussed in the last slide about the metering CT, the other one is protection CT. Protection CT are designed to measure the actual currents in the power systems and to produce proportional currents in their secondary windings, which are basically isolated from the main power circuits. These replica currents are used as inputs to protective relays, which will automatically isolate part of a power circuit in the event of an abnormal or fault condition therein. yet permit other parts of the plant to continue in operation. Well, you can see if any protective instrument will shut down all the plants, that is not feasible, as we studied in our first lectures that selectivity is the important trait of any protection equipment. Well, protection CTs, these CTs uh, are concerned with a wide range of the currents from acceptable fault settings to maximum fault currents, many time normal ratings. Well, larger errors may be permitted, and it is important that saturation is avoided wherever possible to ensure positive operation of the relays, mainly when the currents are many times the normal currents. Well, polarity plays important roles when connecting to relays, as you can see in the figure that there are primary winding and secondary winding. Well, this will determine correct operation or not depending on the type of relay. The terminal of the CTs are marked by H1 and H2 on the primary and X1 and X2 on the secondary, as you can see in the figure. When the current is flowing from H1 to H2 in primary, then the current in the secondary must flow from X1 to X2 throughout the uh, external circuit. In the last slide, we have seen about the polarity of the CTs. Well, there is a test known as DC click flick test that basically determines the exact location. So, what's the procedure? Connect the positive of the voltmeter to H1 terminal of the CT and the negative lead to the H2 terminal. Uh, Connect the negative terminal of the battery to the X2 terminal of the CT. Momentarily touch the battery positive terminal to the X1 terminal of the CT. Secondly, closely watch the needle of the voltmeter. It should jump in the positive direction. This happen in a fraction of seconds. So the meter must be monitored very closely. If the voltmeter kicks in a positive direction, the polarity marks are correct. If it kicks in the negative direction, the polarity marks are incorrect. As we discussed earlier, that the CTs uh, can vary on the basis of the ratios. Uh, it basically deals with the ratio of 5 and the ratio of 1. For example, there is a chart shown in the slide. Basically, it depicts if we can see the first one, 50 is to 5, and the second one, 100 is to 5, and 150 is to 5. These all are the types and the basically differ on the basis of ratios. As per our need, we select these CT ratios, but there is a problem uh, with these ratios, which is known as the ratio error of a CT. So, what is the ratio error of the CT? Uh, it is basically defined as the ratio of the magnitude of the difference between the nominal and the actual ratio with respect to the actual ratio. It is observed from the equation that is of phase angle error that it depends on the magnetizing component of the exciting current. Well, there are some important terms that need to be understand uh, while reading the CTs. Uh, the one is short-term rating. Basically, short-term rating of the current transformer may be uh, subjected to fault current many times larger than its primary rating, and therefore it must be able to withstand the effect of this current. We can say uh, the maximum current which it can carry without mechanical or thermal damage is known as short time current. Well, usually the time is specified is usually 1 or 3 seconds. Well, the second term uh, is the burden, or in many other literatures, it is written as burden rating. So, burden of a CT is the maximum load in VA that can be applied to the CT secondary side. The burden can be expressed in two ways. The one way is uh, it can be expressed as total impedance in ohms of the circuits, uh, or uh, the total volts ampere and the power factors at a specified value of current or voltage. Like uh, burden and short time rating, uh, there are two more um other factors. One is class. The class designation is an approximate measure of a CT's accuracy. The ratio error of a class 1 CT is 1% at rated current. The ratio error of a zero point 0.5 CT is zero point 0.5 or less. So there are two other different cases, like for metering CTs, the accuracy class is typically zero point 0.1, zero point 0.2, zero point 0.5 at the rated current. Well, in the case of protection CTs, the accuracy class is typically you can say 5p or 10p. And the second one is ALF, that is accuracy limit factor. Protection CTs does require an accuracy limit factors. Uh, the ALF is the multiple of rated current up to which the CT will operate while complying with the accuracy class requirements. The common accuracy limited factors are 5, 10, or maybe 15, 20, and 30. Uh, if we talk about the specification of a CTs, that is written on the data sheet, so you can see if there is a notation written like 15 VA class 5 P20. So how you can read the 15 VA is basically depicting the burden rating of a CT. Well, the class 5P 20 is showing that CT will not have more than 5% error at 20 times the rated current. Well, there is a practical nameplate of a CT. As you can see, there are multiple factors that is written on the nameplate of a CT. You can see on the right hand topmost side, the CT type is written. Uh, Along with that applicable CT standard. On the third side, there is a SF factor, that is basically a safety factor, and along with that, there is a ALF factor, accuracy class. So basically, uh, the major reason uh, to show this nameplate, that to get familiarize the student from this nameplate, that if you are selecting any CT, you have to know all the different type of factors that is basically responsible of a CT's performance. Well, that's all from the CT's lecture. If you have any question, you can ask, or thank you very much.